Good afternoon, my dear kids. In today's class, in the laws of motion chapter, we are going to discuss about the concept of tension, spring force, and monkey climbing. So, what are the conditions related to this? Then we'll go for the related numericals related to normal contact, tension, then spring force, and the monkey climbing a rope. That one for all these situations. Let me start the class. Now let me take a certain string of certain length. Okay, what is this? This yellow color one. Yellow color one is a rope. Okay, fine. So now I'm going to suspend a block of certain mass. Then what are the first? Okay, we'll do one thing. I'll take a smaller one. Okay, we'll. Yeah. Now I think this is quite normal now. So what you should do? I'm asking you, take one string. All of you, string means thread. Take eraser, then tie to it. Then hold that one end of the string at this particular point. Then what is the state of string? You are going to call it as a tout. Let's call it tout. So what is the state of this block? The weight of the block will act vertically down, mg. Then if the block is at rest, then who will balance this weight of the block? Definitely it should be tension. So there should be some force. So here the force set up in the string is called as a tension. And how it will act? It will act in this way. Agree this. So now what is the T? T I am going to call it as a tension. Now what is the tension? How to define tension? Tension, a force set up in a string. A force set up in a string, that one. So tension is a force. Okay, next questions are like can you say anything about tension? We are very new to it. Okay, regarding tension. So the first point is I'm going to put what is the nature of it? It's electromagnetic in nature. It's electromagnetic in nature. It always acts away from the body. This is the nature of it. It always acts away from the body. So there is a one condition. Then sir, what else? Still only this much. Further we have it always acts tangential to the string or rope. Here string, rope, thread, both are same. So of all very put, it always acts away from the body. This is something very, very, very important condition, which will be using in almost all our numericals here. And sir, what about electromagnetic force? I'm saying that when it's electromagnetic force, it's like a similar to molecular force. So it's a electromagnetic in nature. Sir, what do you mean by electromagnetic? Both electric and magnetic fields are responsible for it. So it's electromagnetic in nature. Next, sir, can you say anything about like a direction? You are saying it always acts tangential to the string. Next again, it is set up by, it is produced by pull force. When you hold two ends of a rope and pull it, the string will become taut, and the force set up or the force produced is like it's a pull force. So these are the one very basic fundamental things regarding the tension is what I'm putting forward here. So and say like you may feel something this is a new thing, just I think very quite natural. How to show this diagram? This is a block. So instead of this suspending, no, you hold it with your finger, just tie it to finger. That's all, no? So this will be, you take a string, put knot on your finger, then suspend it, suspend eraser or some object. Then what is the state of the string? What is the state of this eraser? Will be at rest, its weight will act. Who will balance it? The tension. Okay, very simplified approach here, nothing big. The tension, the string will balance the weight of the block here. And now one more thing, like if tension is 0, the string is taut. If tension is 0, the string is said to be taut. In this one only, if tension is non-zero, if tension is 0, the string is said to be loose. Okay, there's a one basic condition is what we are defining. So what do you mean by loose? Like suppose say if you don't suspend anything, let me take the same diagram. You remove this, then how the string will be okay. So I'll some of you are saying sir not seeing it properly. Okay, got it? No? Tension. So this one is called as a loose, string is loose. This particular string is called as a taut. I'll give all the examples. This is very important. If you start checking, no, you can see that one. Almost every numerical we do encounter this tension. The concept of tension is very, very important. So just it's like a string. So like what is this? There's a thread, string. It's left to you. Whatever you want, you can call that one. Okay, I get this. So there's one very basic idea of the regarding the tension. Okay, let me give all electromagnetic nature. I can't say much about this. You select the gravitational force. It's an electromagnetic nature. Due to interaction between the molecules, this will come into picture. So it's electromagnetic nature. It always acts away from the body. You see that one. At this end, the tension will act here. At upper end, the tension will act in this way. Then there's what this rope is doing is try to pull down. Definitely what this rope is trying to do will try to pull your finger down. So therefore the tension force I'm showing it. So this end of the rope is trying to pull the ceiling down. Then what do we get? We get here a reaction. So again, what is the state of this? There's a ceiling. Everything is a ceiling. Then what is R? R is equal to again T. So let me write R minus T equals 0. R equal to T. For block is at rest. T minus mg equals 0. T equal to mg. What is the tension in the string? What weight you suspend the block, that much of force equal to mg is what will be set up in the rope. Okay, sir, like we have seen something of like this also. What is your interpretation?
Sir, what is R here?
R is a reaction, reaction.
Okay, sir.
Sir, it will have normal also.
R is called as a reaction. The string will force will always occur in pair. So the rope is trying to pull down. The ceiling will exert a force on the rope. That is R. Okay. No. Sir, how you show the tension here? There's a rope. I think we have diagrams here, no? Okay, there's a rope, not a this one. There's a string or a rope tied between two walls. I think to hang close will be using some thread, some string, rope to tie the close. That only I am discussing here, nothing big. Okay, get in this one. So how the tension? Tension will always act away from the body. So show like this. So what is the body here? The walls are the bodies. Then if you take small element, it has become a little bit. Yeah. Let's take a small element. Then how the tension here will act away from the body. Now that element will become a body. You have to show the idea of tension in this way. I'll give a few more. The tension is it's a force set up in the string, that one. Okay, I'll give a few more ideas. No. Okay, let's take another example. There's a rope we have like this. So I have suspended here. I'm going to suspend a block. Then what we notice here again, it can happen, no, like this. And sir, what is that disc? This called like a pulley. Go to medical shop, ask pulley rope, they'll provide this one. The rope will pass it. So what is this? This one is a rope. Rope, string, thread, all are same. Okay, let's analyze here now. What are the forces acting? The weight mg will act. Who will balance this weight? A tension. So how the tension will act here? Away from the body. So the tension here to show it here. The tension at this point will act in this way. Similarly, the tension at this point will act here. The tension at this point will act here. And here the reaction. If you want, you can give something. Let me use word reaction. R. R is not radius. R is a reaction. Okay, there's a pulley. So there's a rope. So we'll get this one. So I will define a small element. Then how tension will act. Tension you have to show that away from the body. Getting the idea?
Sir, R equal to T also.
R equal to T, yeah, here also. There's what is this? There's a wall. So here T minus mg equal to 0. T minus R equals 0. You can write R equal to mg if you want the reaction.
Sir, what is that green part, sir?
Small element,
Okay,
For
sir.
Pulley, nothing will be.
Part of rope.
For
small element on a rope, part of a rope.
Sir, for Pulley, point of contact. will be-
I'm not hearing you. You should come with headphones or something. Not possible. Make observation. What is that green color? Small element. What do you mean by normal force? Fatima, what do you mean by normal force? Something, okay, what is normal force? Where you want, tell me.
Sir, from the wall.
No. Just like, see, this rope, see, very simple. Please don't think very big and just tie rope and try to pull the, take some nail. To the nail you tie thread and try to pull that nail with the thread. That's what I'm discussing here.
Sir, but there also normal force will come.
If you connect a thread to it, so there won't be that one. The tension force is nothing but the normal contact here. Okay.
Okay, sir.
So like okay, fine, sir, everything, it always acts away from the body. Are you treating this pulley as a body? Yes, for this pulley and body, and it will act tangential. You see that one. Here I'm showing tension like this. For this part, here I'm showing tension. How it is this? Here it's vertical. It's a horizontal. So it will always act tangential. Away from the body, tangential. And what do you mean by taut? Is it taut? Yes, the string is taut, tension non-zero. Is it taut? Yes, string is tension non-zero, taut. What about this? Loose, because there is no weight suspended. Next again, the tension is produced by pull force. What do you mean by pull force? The weight and the R, the ceiling is trying to pull the rope up. The weight is trying to pull down. The resultant of, so these two are what? Pull forces. These two are what? The pull forces. The weight is here, what happened? The mg. It is trying to pull down. The ceiling is trying to pull up. So what forces are acting on the rope? The pull forces are acting. Or you can, two persons, they're standing on the ground. They are trying to pull a rope. Oh. Now what they will do is they will pull this rope. They're pulling each other. So what these persons are doing? Not pushing, they're pulling. It appears like that. They're pulling each other. Two persons. So how do they exert force? This person will exert force in this direction. This person will exert force in this direction. Some red color. Then how the tension? The string will act here in this way. So what is the tension? The tension equal to F here. With what force the persons will pull the rope, that will be the tension. So the tension, the string is what? The force with which the persons will pull, that is what the tension here.
Sir, tension is equal to force only in this case or everywhere, sir?
I'll break your head. I'll break your head. Everywhere. How come you are everywhere? Then what is the use of learning? Just depends on situation, no?
Okay, sir.
So okay, now the persons. Let me just write here. Two persons are the persons are pulling each end of rope the persons are pulling each end of a rope by a force F. Now the tension the rope is the tension the rope is T equal to F. With what force the persons are pulling, that is what the tension here.
Sir, if both will pull with same force, then tension will be 0.
Tension will be
0, sir.
some common sense, like if you pull both the ends, tell me like what is the state of rope? Taut, no. When string is taut, tension should be non-zero. Not plate skipping, huh? Not plate skipping.
Plate.
Never played any skipping with rope.
So if tension will be force.
I'm asking something. Okay, later on will come. Did you play skipping or not?
Yes, sir.
Did you any time did you ride any clothes on the rope?
Yes, sir.
Did you first of all seen rope?
Yes, sir.
Okay then. If you pull it, tell me what is the state of rope. You and your sister or brother hold the rope and try to pull each other. Tell me what is the rope? How the rope will be? Rope will be like this.
Straight.
Straight, no? So it's called as a taut. So when the rope is straight means taut. Taut means what? When tension will be there. What you mean to say is a net force on the rope? Yes, it's 0. But there will be tension in it.
Okay, sir.
Everyone say, I'm telling you this one, there is nothing called me for me to teach anything very big here. It's all about the rope, string, block, the objects around us. Prithvi, switch off video. Okay, that one. Now this is about the person. So now the persons, instead of pulling the rope, if they push the rope, how it will be?
Loose.
It will become loose. The string will become loose. Loose is nothing but tension will be 0. Here what they do, they will, this rope itself I should remove. Okay, it'll be like this. What they are doing, they're trying to push. Here the persons pushing each end of rope by a force F. So what is the tension? The string is loose. Tension 0. Okay, finish, over. Got it now? So who will set up tension? Pull or push forces?
Pull, sir.
Pull.
Pull forces. This is the very important. You look at the physics textbook. Just keep on turn pages. Almost in every page you see the problem string will be there. Almost in every page you can see them. There'll be string, there'll be blocks or wedge or ball. A string will be connected and there'll be motion or in rest. So whenever the string is there, immediately the idea of tension should come. Okay, make observation. I'll go for next few more cases, few more things I have to explain. So here the string means nothing but the thread, cotton thread. I think we'll be using very frequently in our home to stitch clothes or something. It can be even threads or cotton thread only, or taking your example, no, anything. It can be of made up of any material. Rope, rod is different, string is different. Please do understand, rod is different, string is different. I don't know, somebody is telling, sir, is it rod? So rod, string, if you don't know, what shall I do? This is not a rod, it's a string. Please, all of you, some minimum common sense must be there. Again, rope or string or thread. To hang close is what that string, no, that is what I'm discussing here, nothing big. Okay, now it will act tangentially. Yeah.
Will tension be opposite to the direction of force?
What do you mean by that? See, like here, is it your, suppose you are holding this, your finger, string and block. All this is your body, or this is a part of your body, this is the string, this is a block. You tell me.
Only hand is the part of
How, part of body. How many bodies you are seeing? How many different bodies you are seeing? Different bodies I'm
two.
telling. Huh? How many?
Two.
No, look at how many bodies are there. Your arm, string and this block, no, all three are different, no?
Yes, sir.
So tension in the rope means you think about only this. Tension in the block, wrong thing, no. Who will balance the weight of the block? Tension, that's all. Don't say that tension in the block, tension the string, that's all here.
Okay.
Now how come you say that tension is opposite to F? Okay, you're looking at the diagram, you're telling. What is the tension in the rope? T. This F is what? Person is pulling the one end of the rope. At end of the rope is what this F is acting.
Yes, sir.
So
Got
we'll
it.
pull that one. Okay, this what we are discussing is we are just discussing the from one end of the rope to other end. At one end I'm pulling the rope. Okay, no doubt. I'm holding the rope, I'm pulling it. Then here what happens? F will balance T.
Okay, sir.
You have to hold one's rope. That is the major problem. Purchase one rope, go there, 30 rupees plastic rope will come, tie to any door, window frame, try to pull it and analyze, make observation.
Excuse me, sir.
Now we can have a situation like the string will be like this. Then I am applying here. The rope itself, what happened can be in this particular form. I'm trying to pull it. No.
But some sounds are coming.
I'll hold it and I'll start pulling it in this way. Then how the tension will be acting. Suppose this is a tout. This is a tout. So like if you pass over some spear or some object like this, we'll keep it and I'll start pulling it. Some spherical object. I kept on some spherical object. I start pulling the ends of the rope in this way. Then how the tension? So I said like a pull forces. These two are what pull forces. So this is the rope. This is some ball. Yes, you can take it like this in the face. So sir, can you show the tension as it will be? Then if you take this is the small part. If you take this is a small part, I can't see it. I'll bring it here. If you take this as a small part, how the tension we have to show it? It should always act tangential, no? So here you have to show the tension in this way, not horizontal, tangential. For a circle, if you draw a tangent, how it will be? Tangential to it. So it all depends upon how that string will be. If the string is like this, how the tension. So here let it be this one. I am applying a force F. This is F, axial force. Then the tension here should be in this way. So the tension will always act tangential. That is the one golden rule. If it is vertical, already we have seen how the tension will act in this way. If it's horizontal, how it act? Tangential to the rope. Tangential. I think now you got the idea. Tangential along the length of the rope, it will act. You have to show that. So how it is a curve, no? So therefore you have to draw a tangent to the rope. Whatever the shape of the rope, the tension should be directed tangential to the rope. Who will pull this? These are the pull forces. Okay, pull force I'll show by black color. Now you'll get confused again. Okay, fine. This is about the basic idea. Okay, let's take some example.
Sure. Thank you, sir.
Let me take it's a simple example. I have this one, so let me bring 3 blocks.
Sir, in the hour diagram, it's tension or force, sir? Right side one, top right.
Oh, I didn't right. Okay, T it should be, yeah. Yeah. We have a string. The string I'm showing by brown color. Instead of showing by thick, I'm just showing by a brown color line. That is the string. I'll pull this block by force F. M1, M2, M3 be the masses. This is a surface, smooth surface. You might have played this when you were a kid. Toy train. The toy train is what we are discussing. We have to calculate now what is the acceleration of the block and what is the tension in both the strings. Now when you pull the block M1, will M2, M3 will move or only M1 will move?
All three
All
will
will.
All three will move, sir.
will move, no? So these are very basics of basics, sir. You tie 3 blocks or anything, 3 toys, then you start pulling this will also move. And what is the acceleration of all? Must be same. The acceleration of all blocks must be same. Then I'm holding only this one. I'm pulling only this block M1. Why do M2 and M3 will move? Who is pulling them? The tension. From here is what the ideas will come into picture. All of you listen again. Don't add any chorus to me. Just happily listen to me. Let everyone, let only what my teaching, let them listen. So I'm only holding the block M1 and I'm pulling it. Then what makes M2 and M3 to move? The tension. So now we know the tension will always act away from the body. This is T. The string will be taut. Then this tension, let me call it as T1. Then again this string will be taut. This is T2. Tension should always act away from the body. You can see here T1. You can see here T1. Okay, this is T2. Okay, this is T2. Then let's write the equations of motion. F minus T1 equal to M1A. T1 minus T2 equal to M2A. T2 equal to M3A. Then let's add up all these equations. What is the net force acting on this system of block? F only. But what about this? This will become internal to this system. If you look at everything, plus T1 minus T1, plus T2 minus T2. What is the only external force acting? That is F. So that you are getting it. You can, if you want, you can write directly. This is individual. You see that one. Sir, how come you write F positive? This is T1 negative. If a force acts in the direction of motion, positive. If a force acts opposite to motion, it should be negative. T1 acting in the direction of motion, so positive. T2 opposite to motion, negative. T2 is acting in the direction of motion, positive. Opposite to direction of motion, nothing is there. Okay, only T2 I am writing it. Okay, I got the acceleration. That let me substitute here. So what is T2? Similarly, I want expression for T1. It's left to you. Either one you can substitute. Let me M1. So what is A? F by M1 plus M2 plus M3. T1, we wanted expression for T1. So F minus look at here, both the tensions in both the strings will it be same. String 1. Can you really see, can you visualize tension? You take a rope and start pulling it. Can you see the tension?
No, sir.
No way, no. So make things clear. Make observation. So I'm able to see, okay, well and good. Show that technique to us. It will help everyone. So this tension will not be visible, but we can measure it. How you can measure, sir? I know what force I applied. I know what are the masses. We have instruments which can measure tension distribution. Later I'll explain. Time being. Okay, like this, the tension the strings. So what about tension both the strings? Will it be same? If tension were equal in both the strings, how come block will accelerate? So definitely T1 must be greater than T2. That you can see it. T1 greater than T2. What are, can we put condition like this? F greater than T1 greater than T2. Must be, no, then only it will start accelerating. This force must be greater than this T1, then only it will accelerate. This T1 should be greater than T2, then only this will accelerate. I think we should make observations. Okay, write it down. Now a situation is there like this. There's a rope.
Sir, F minus T1 is the force exerted by the second string, sir, in between them.
What you want to ask clearly?
No, sir, how to find out the force between two blocks, sir, exerted by string.
You ask question clearly. Still.
Sir, there are how to find the force between M3 and M2, sir?
That is T2, no? Are you not saying string 2? And what is the tension? T2.
Okay, sir.
No, there's a rope. You pull the rope by a force F. Then how much of tension the rope will be? We are going to pull it. I'll pull the rope by a force F. I think there's a quite natural type thing. With what force you pull the rope, that will be the tension in the rope. There will be the tension in the rope. So the tension in the rope will act here. The tension here will act in this direction. Then the weight of the person will act. The person will press the ground, so the ground will exert a force, Ng. The person will be holding and will pulling the rope. Tell me, like, what are the forces acting on person? On the person, the forces acting are, if you like a Mg, I'll write it. So only on the person. I can't draw again the person. The forces acting on person, or we'll draw the free body diagram.
Ng and T, sir.
The forces acting on persons are this much. The person is holding rope, no? So therefore now what will happen, with what force will pull the rope, that will be the tension. So now what is the tension in the ring? Tension in the rope. The tension with what force? The person pulls the rope. With what force the person pulls the rope, that will be the tension set up in the string. Then what is it? T must be equal to F. Therefore, T equal to F. So then what is the equations? Ng plus T minus Mg equals 0, or Ng plus F minus Mg equals 0. So what is normal reaction by the ground? Will be less than its weight. This Ng we can measure with instrument. There I can see that if I pull with more force, definitely. This is a very important small information, but very, very useful for us. So with what force you pull the rope, that will be the tension in the string. If you pull the rope with a force F, that will be the tension T.
Sir, then can we say that tension is the opposite reaction force of our normal force, sir?
Shall I give Nobel Prize for you?
Why, sir?
Why you are bringing unnecessary things? No, not like don't say reaction. Reaction word is something different. I'm pulling the rope. I'm
Sir,
pulling the rope.
if we apply force more than Mg, will go up, sir.
Yeah, if you want to climb up rope, what you'll do?
Okay, sir.
See, these are the. That's what I'm telling you. No, the more things, if you know general, it'll be very easy for me to teach convince physics. If you want to climb up rope, what you should do? You should apply more than your weight, then you'll climb up.
The force you apply is the tension on the rope.
That's all. With what force you pull, that will be the tension. Okay.
Yes, sir.
Purchase one rope, what is there? 100 rupees. You'll be having so many window frames there. Tie it and try to climb. Who will stop you?
Rope will break, sir.
I'll break your head then now. Okay, so what is this? This is a normal reaction by the ground.
Sir,
Ah,
sir, the force is acting opposite to NG, no, sir.
what force?
Sir, the force with which you are pulling, sir. It is opposite to the normal contact force exerted by the ground, no, sir.
NG, huh?
Yes, sir. NG and F are in opposite directions, I'm saying, sir.
F is something will exert a force. I have to show that F no, otherwise how tension will come.
Okay, sir. Okay, sir.
Tell me this F, sir, why you are not showing F on the rope? One end of the rope I am pulling down with my arm, the string will become taut, a tension will act. So on the what force? Now you have to, on the person means you have to show like this. Don't show F on the person down.
Okay, sir. Okay, sir. Understood, sir.
Sir, I have a doubt, sir.
Yeah.
Sir, if the force which we apply to pull the rope, sir, if that will be greater than our weight, sir, that time it will become negative now, sir, normal reaction.
You will start climbing up, my dear. You'll start climbing up.
Sir, but the normal reaction will be negative now, sir.
I will, if you were in class, no, I would have, really, I would have scolded like anything. I'm telling that you are going to climb up, my dear.
Yes, sir.
Never seen such things. Very sad.
Seen, sir,
Very
seen,
sad.
sir.
Very sad. Very bad this is. Okay, now this is about the regarding the tension. So now we'll do one thing.
Sir,
A
one
person
minute,
wants to,
sir. Yes, sir. Thank you, sir.
now the same person will ask him to climb up the rope. Then we'll see what conditions will arise. This person only is going to climb up. It's going to climb up. Is having a weight mg. Then what are the conditions for him to climb up the rope? So first of all, his weight will act mg downward. Now what is to? He should hold the rope tightly. No, there. He should hold the rope tightly. Then he should start climbing up. Then he should start climbing up. Okay, sir, fine. Like, we'll do one thing. I'll apply oil to it. Then I'll ask you to climb. Possible? Not possible, no. Any reason? Because there's no friction. So what actually happens is like, there is some sort of frictional force between your palm and the rope here. The person, what happened because of that friction, is able to climb up. Because of friction is able to climb up. So how that friction here is what the beauty of this climbing of the person will come into picture. Make observation. Here we just say tension. In the books they are given like this. There's a tension. And the tension will act away from the body. In fact, you better take it in this way. A friction will act here on the person. The frictional force will act. I'll show. I'll take a little bit. This bigger one to show forces. Yeah. It's not a lizard, some person only. So he is climbing up. Then Here what actually happens is like the friction on the person will act here. I'm showing things very clearly, please make. And in turn the friction on the rope will be like this. This friction what it is doing is trying to pull the rope down, then nothing but a tension will come into picture. Let's show by. If you take only the person, what are the forces that are acting? Means suppose a person is at rest. Then how you write only the person? Okay, I'll bring the person separately. This what? Then if you bring the rope separately, let's see that. Now, what is the state of rope? It is a taut, no? Why it is taut? Because the friction here is some sort of acting downward. Now the string has become taut. So a pull force is there. Sir, how come only one force? At other end there will be a force acting. Then here the tension will be there here. Tell me what are the pull forces? Here the friction is trying to pull it down, the rope. At other end, the ceiling is trying to pull up. These two will set up a pull force. Because of that, the string will become taut. So what is the state of this string? It will be taut. I have to show tension here also. Got this idea now? So here in the books, what happened is like, now this F is what they removed. That is they're telling that this tension is acting. But this is the basic idea. Individually, if you analyze the force acting on the person and the rope, why the string is taut? Because see, what is the basic necessity? The string will be taut only due to pull forces. Which part of string will be taut? Only this part from where is holding. This will maybe confusion. Okay, some students are getting confusion. I have to show this friction here. It's not on person, on the rope. Let it be here. Now, which part of the rope will be taut? Only this part. The remaining part? No, it will not be rope because nobody is there, no, here. Getting this one, this part will be taut. I think you might have seen many programs or something you might have tried where this part will be where you are holding the rope from here to here will be taut. This lower part will be loose. So why means don't ask, because nobody is there to pull down that one. There's no pull force from in the lower part, so no tension here. So this part will be taut here. Now what is the tension in the string? This F. Now the person is at rest. For the person to be at rest, so what is the F minus mg is equal to 0. Then on the string is taut. Okay, so net, how will write here on the string? What is the equation? T minus F equal to 0. So finally, what we can write? T is equal to mg. This is a basic idea here we have to bring. But sir, is it tension acting on the person? No, the friction is acting actually. The previous problem I wanted to explain, but everyone will get confused, so I brought it here. Now the exact explanation is what I am trying to give. Okay, got it now? So now you apply oil and try to climb. It will become slippery. Not possible because there won't be sufficient frictional force and you can't climb up. And now if the person starts pressing hard more, how do this friction will come? How much hard you press the rope. How much of tightly you hold the rope. And you will start pushing up yourself. Okay, now the person starts accelerating. What conditions will come here? Next condition, the person here, he will start accelerating. So person at rest. What is it, this first case? Person at rest. Here, second case, person climbing up on a rope. Let's see what conditions are there. Okay, now what we can write here is climbing up the rope. Then what is the equation we can write? F minus mg equal to m. F minus mg equal to a. And we know on the rope, this F minus t equal to 0. So finally, what is, we can write T minus mg equal to ma. So he's climbing up the rope with an acceleration. So T equal to mg plus ma. So what is the tension in the rope? Equal to this much here. Similarly, we can make a situation where person is climbing down. Maximum try to analyze very practically. It will be very easy. On paper, see what all we can do. Nothing is there. Just as some basic idea, if you have no, little bit easy. You can pass through this all these topics very easily. Now in this case, mg minus f equal to ma. On the rope, what is the equation you can write? So tension should be like a by pull forces. Okay, this F is what pulling. What about other force from the ceiling will come. Now from ear to ear, can you show the tension like you have to show away from the word. This ceiling is like one body, so tension here. This person holding here also you show the tension. Got it now? That's the same thing here. So if you want, you can write here R, no problem. No, finally what you can write here, mg minus t equal to ma. What is the tension here now? Mg minus ma. So if you want to climb up, what you should do? Now, what we have to do? Yeah, it is there, no, climbing down. Now, if I want to stay there only on the rope, I should press the rope in such a way that the frictional force acting should balance my weight. Or the tension in the rope should be equal to my weight, indirectly. I should press the rope so hard that the tension should balance my weight. Now what I should do, if I want to climb up, what I should do? I should press the rope hard. Okay, that one. And I should try to climb up such that the tension in the rope, if it is greater than weight, then I am going to climb up. If I want to climb down, then slightly open, I should see that I should not press the rope so much. Okay, still there should be some friction between me and the rope. Then I can, and if the tension in the rope is less than my weight, I'll start climbing down. This is what in the books we do explain things.
Sir, here press the rope means we should press it downwards so that we can move upwards.
Sir, can we take here M common, sir?
M you can take common. Press down, press up. Oh God, like climbing up rope, don't know. How you climb up? Just by pressing will you climb up? What you should do to climb up? What you should do with your fist there? You'll hold rope, no? So you are going to move your arms, no? To move up. Climbing up rope, say I can't show here the climbing up the rope, only one diagram is there, please do understand. How you climb up the rope? Just if you press it, will you climb? No, you are going to move your arm, no? You are going to move your arms up and by holding the rope. So when you press hard, what happens? The tension will become greater than mg and you will start climbing up. Just by mere pressing you can't climb. Okay, please do understand some, or else watch some video, or else you climb the rope. Instead of man, if I had a tail, one tail, it will become monkey climbing up. Okay. If I just bring one tail here, it will become monkey climbing up. Climbing up rope, I think everyone knows some basic thing how to climb up the rope. There, when you are climbing up the rope, what you have to do, if first it is here, first you are there. Now to want to climb up, what you have to take this right arm, you have to hold it here, then press hard, then start moving your body up. Then the tension, the string will become little empty and you'll start climbing up. Then this left hand again you have to keep it here, above the right arm. Then the right and left arms, you should alternate one above the up, one above the other. Then you can climb up, no? I think there's a method. Not understanding, then you have to visit some places where climbing up ropes are there, go there, work out. Okay, now we'll have a introduction to spring balance.
Sir, one scroll up, no, sir. Sir, it should, in second diagram, it should be T minus F, no? Sir. In second diagram.
Minus T minus mg.
On the rope, it should be T minus F is equal to 0, I'm asking, sir.
F minus T or T minus F? What is it? You mean to say this one, no? It doesn't matter, no? I'm just equating forces here. Equilibrium, no, it is. Okay, yeah, no problem.
Okay, sir.
It's equilibrium, no? Therefore, I'm just equating to 0.
Oh, okay, understood, sir.
Huh?
Understood, sir.
Yeah. Now some spring balance, I'll introduce to idea of. Spring balance, we will take this one. This is now, I think, weighing scale. A good example nowadays, we can, in ohm also we can weigh, no? Like 10 kgs, 5 kgs to measure that particular weight, or when we'll be having a spring. No idea, just at least watch something. So we'll be having a pointer, we'll be having a scale. This will be a pointer, and here a spring will be attached to it. From the behind, a spring will be attached. Depending on the weight what you suspend, the pointer will be pointing at that one particular position. Sorry, the spring will be to this position. Just I'm giving rough diagram, very rough diagram. Yeah, it'll be, and this will be the pointer. Red color, where it is. Yeah. Based on that, the pointer will be moving. Okay, we'll bring pointer here. That'll be better. This is called a basic spring balance. Purchase 150 rupees. It is available. So they'll get a better picture. Or you can construct your own also. So what is the spring balance? It is used to measure the weight of a body, of any bodies. Like, depending upon the spring balance, measuring capacity you can purchase 100, 0 to 100, 0 to 10, 0 to 5. It all depends on the, for household usually we'll go for 0 to maximum 5 kgs. Like this you can hold it and you can measure. Just like you can, instead of block, what they give, they'll give an like some sort of a hanger here. So anything you suspend to that, you can measure the weight of it, and here the scale will read. That's what the spring balance, what I'm discussing. Many spring balance are there. There's a very general basic one I'm discussing here now. Okay, now What is the spring balance? So here I will just show it like this. There's understood it's a spring balance. Agreed? The spring balance will show by yellow color. And then what is the reading of that? How it will be? So you can proceed like this. The string will be taut. Why it will be taut? Weight mg will act. And here the tension T. The reading of spring balance is nothing but you just show this tension. There is a reading of the spring balance here. So what is the reading of spring balance? Now what is the state of this block? It is at rest. It is at rest. So what we can write? T minus mg equal to 0. Then what is the reading of spring balance? Equal to reading of spring balance is equal to T, which is equal to mg. How much of here force acting? That is only what spring balance. Sir, what actually spring balance? Spring only, like spring force will act here. It will reach certain value. Let me give one more example. Here I am suspending a block. So I want the reading of this spring balance. These are pulleys. These are called as the pulleys, light pulleys. Pulleys are light.
Sir, once can you scroll a little bit up, sir?
Yes, sir.
I think we can see everything. Okay, now let's get into the discussion here. So here the tension, the string, all strings are ideal. All the strings are massless. All the strings are ideal. Ideal means here massless and inextensible. There's a one very generalized. If I mention, you take it. Otherwise, by default, we assumed it. They are massless and inextensible. Then what are the forces that will be acting? Here mg, tension T. Then this pulley is light, the net force on it should be 0. So here how much of tension? T by 2, T by 2. Here tension T by 2. Tension should always act away from the body. So how much here? T by 4, T by 4. How much of tension? It has to be here T by 4. Now this is what the spring balance. Then what is looking at the lower block? What is the state of it? It is at rest. Then what is the equation you write? T minus mg equal to 0. Then how much of spring balance, reading of spring balance is? Nothing to do. Okay, make observation. We'll take the next conditions. Okay, now we'll.
1 minute, sir. Okay, sir.
Sir, can you once explain why the reading of balance is T by 4, sir?
That's what the tension there it will act. What is there in explanation? Huh?
Okay, sir.
This is a pulley. So this is a rope which will pass on it. This is a block. Okay, this is a block is having mass m1. This m2. Let's analyze the motion of this one. So what is the pulley? Pulley is just connected to the. Hope everyone having some idea. Pulley. It's like a wheel, no, where the string can pass over it.
Yes, sir.
Yes, sir.
This one. Okay, now let's analyze the motion of this one. What are the forces acting? The first, the weight will act, and the weight of this will act here. The moment you release, let's see what will happen. This is like a surface, like a table. On the table, I fixed it here. Then the string will become taut. The weight will act. The string will become taut. How the tension? Tension should act away from the body. So here the tension. On the pulley, I have to show tension away from the body. Then on the block M2, the tension should be like this. Now this will, here the normal contact will act. Sir, are these two in contact? S. Show it all. Nothing wrong. Huh? What is N2? N2 is by the block on the surface. What is this N1? By the block on this vertical surface. Now let's see what will happen. This will accelerate. Then the equation here will be T equal to M2A. M1G minus T is equal to M1A. M1G equal to M1 plus M2 into A. So what is the acceleration? M1G by M1 plus M2. This is very important. Sir, how you wrote this? The moment you release, what happened to block? Will it move up or move down? Will move down, no? This is quite natural. Say, sir, I don't have pulley, what to do? No need. Just pass this rope over the edge of the table like this. You connect one block here. Sir, I don't have blocks. What do you mean by block here? Any box? You take any box,
Any weight.
any weight, or say some stone available. It may damage. Okay, take any box. Then suspend here any box here.
Sir,
Then
M1 greater than M2, sir.
what will be that, pa? What will be that? If M1 less than M2, will they move up? Irrespective, no? The moment you release, what will happen? Whether M1 greater than M2 or M1 equal to M2 or M1 less than M2. This will move down, this will move towards right. Take any box, take one string, pass over like this, suspend any other weight. If you release, this will move down, this will move towards right. Why it happen? The tension will make it to move. Here the weight is greater than tension, it will move down. That's all. What is the acceleration of this system? We have this much here. Then what is the tension? I'll substitute this value of phi back here. T is equal to M2 M1G by M1 plus M2. There is a tension in the string. And what is the here? This pulley is light. What about this string? String is also light. Light string. Very, very, very important. Those who are not understanding anything, please. Thread will be there, eraser you keep it, some box you tie it, you suspend or this pulley not there, let it be, no problem. Just leave it here, suspend it. Just make observation. Oh, this is what happening. Then come back and analyze. But this is very important. Now, let's go for little bit some practical. You take any object, will it have a mass or massless? You take any object, should have a mass. So it should have a mass. There's no other way. So even this string also, what we say here, will it have a mass?
Yes, sir, but negligible.
Okay, let's take a rope which is having a mass m. And let L be the length. So here m is mass of rope. Then I want the tension in the rope. Let's see that. And how to show all that one. So what is m? M is the mass of the rope. So what I do is like I'm going to assume a small element. That small element will bring it here. Then that small element will have mass. dm into g. Then who will balance the weight of this small element? The tension. So therefore here the tension slightly at this point it will be T plus dt. Slightly be more. Here it will be T. So how you are showing this? Because the net force should be 0. Then who will balance the weight of that element? The tension. So the tension just above the element should be slightly greater than that below the element. So here we have a distance x.
Sir, what is DMG, sir?
DMG, mass of that small element. So let the length of this be dx. So I'll define dm. dm is what? We'll define one more quantity, lambda. Mass per unit length. What is dm? Lambda into dx. I think this will become lambda is m by l. So how you define this one? A rope of length L, how much of mass it will have m? And this end is defined as x equals 0. This is x equal to L. So if the rope is having a mass, then we define like this here. What is the tension at this point? Yes, now we calculate. So now let's come for this one, for small element. For small element, the equation is t plus dt minus t minus dmg equal to why t plus dt? It is acting upward positive. Why t here again negative? Downward. dmg negative y downward. And what is the state of the small element? The entire rope is at rest here. This is what happens practically. This is what happens practically. Then finally, what do we get? dt minus dmg equal to 0 or dt equal to dmg. dm is what? Lambda dx. Now let me go for the limits. Now, what is the basic idea? The tension is set up by a pull force. You all know the tension is set up by a pull force. Is there anybody below here to pull the rope? Nobody is there. So therefore, what should be the tension here? The tension here must be 0. Because the tension is set up by pull force. Is anybody is there at the lower end to pull the rope? Nobody is there. So therefore, the tension here should be 0. So then the limit will be at x equal to 0. The tension is 0. At a distance x, let t be the tension. Then what is the expression for finally the tension? Is equal to t equal to lambda g okay, this is the expression for the tension. So tension at a distance x given by this one. What is the tension at highest point? At lower end it will be 0. So let me bring A and B. Tension at A should be 0 because x equal to 0. Tension at B. What is lambda? M by L. What is M? Mass of the rope. This is very simple. You take a rope having a mass. You hold it at upper end. What you feel? You feel weight of the rope, no? The whole weight of the rope. Simple analysis. I'll draw the diagram. Like this, you are holding the rope. Here is the rope. Now, will you feel the rope is having certain mass? Let's assume. Will you feel the weight of the rope? Yes, you feel no. So what you feel that you are holding the total weight of the rope. Now, if you hold here, you feel that you are balancing its weight. Very simple. So therefore, what you feel tension here equal to its weight. You hold at this point, then you feel half of the rope is what you are holding it. Half of the weight of the rope will come into picture. So how much of weight you feel? The weight of the rope is what you feel. So tell me what actually happens here. I'm holding a rope. What actually happens here? Again, the friction idea will come into picture. We will balance the weight of the rope, the friction. Then the friction on the person will be downward. The person should exert through his muscles. He should balance that friction force. It's somewhere here. Okay, that will be more difficult in the friction chapter. We'll analyze in detail. Now, time being, who will balance the weight of the rope? The person. Okay, therefore, what is it for rope having a mass? The tension at highest point equal to the weight of the rope, and the tension at lowest point will be 0. So now I think we have to be alert. Rope having a weight. Rope is massless. Let's not bother. If the rope is massless, then the tension everywhere will be 0 here. So for rope having a mass, then the tension will be different at different points. So what is the conclusion? We'll make it. I think the diagram belongs to this one, no? So we will shift it here. Let's write comment for light rope. I'll write it here. For light rope, tension is constant at all points. For heavy rope. Heavy rope means which is having a mass. Tension is different at different points. Light in the sense massless here. Okay, write it down.
Sir, for light rope, tension will be negligible, sir.
Negligible, or better say, yeah, will be negligible here. Say, we'll never get a rope massless, only on paper, massless we say. Okay?
Okay, sir.
Let me
Sure,
give.
on the Sir, here tension lambda gx is the tension at that small piece, no, sir?
Yeah.
The tension here it is equal to lambda gx, no, sir? That is equal to that small piece, no, sir? Means at the small piece.
Yeah, here, at this point, for small
That
element.
green piece. Yeah, okay, sir.
Means as you move away, tension should increase, no? So here T means just above the element here, it should be T plus dt. Because who will balance dmg? Tt get cancelled. So who will balance dmg? The dt.
dt, yes, sir.
I will suspend a block. This is having a mass m1. This, or we'll directly do one thing. We'll take value. M1 equal to 2 kg. M2 equal to say like a 3 kg.
Sir, numerical, sir.
Numerical. These are the points A and B. Length of the rope BL. 10 meter. At 3 meter. This is say at 7 meter or 6 meter. 8 meter I'll take it. Yeah. We have to calculate tension at various points. Tension at points C, A, B. What is the rope? mass of the rope is m1 and length is L, and a block m2 is suspended lower end. A rope having a mass m1 is suspended vertically, and a block is hung, and a block of mass m2 is hung at lower end at equilibrium. Find the tension in the string at points A, B, C.
G value how much?
10.
Okay.
If I give 9.8, otherwise by default you should take 10. Tension at C should be M2G. M2 is how much? 3 into 10, 30 Newton. Tension at B. What is the lambda for the rope? M1 by L. So that should be equal to 2 by 10, 0.2 kg per meter. So tension at the B, what we should write? The weight of the rope, lambda into 3 into G plus M2G. You find little bit difficult, I can show you small diagram. The weight of this part of the rope will also act. Getting no, this the tension this point is weight of this part of the rope plus the weight of the block. M2 is equal to 3 into 10. 10 to ja. Okay, this will be 2 3 ja 6, 6 plus 30. Tension at point A, lambda into 8 G plus M2G. Tension it is, sorry, it is. Get you know? So if the rope is having mass, then tension will increase from lower end to upper end. What do you mean by mass m1? The mass, this part of the rope, tension at this point will be only due to this. It's very simple. If you hold here, you can feel this weight and this weight only. If you hold it here, you feel this part of the weight of the rope and this one only. you are going to hold it. Though it's suspended, you hold it here, you can feel only this part. The other part will be loose. If you hold it here, you feel this part of the rope plus this weight of the block, you can feel it. You are supporting it. That's what I'm discussing.
Excuse me, sir. Sir, what is 8 and 3 in the diagram, sir?
What is?
8 and 8 meters and 3 meters.
Length are you not seeing?
But sir, you give length is equal to 10, sir.
My dear, the point A is at a distance 8 meter. The point B is at a distance 3 meter.
Okay, sir.
Huh?
Okay, sir.
Yeah.
Sir, so to measure the whole mass, weight of this total system, we need to
Yeah, you hold it
imbalance
here.
at the top, sir.
Yeah, you hold it there. Then you feel weight of the rope plus weight of the block. Huh?
Yes, sir. Yes, sir.
Let me take the next condition. If this is a ground, there's a rope. I'm showing a little bit big like a block. It's a rope only. I'm going to pull this rope with a force F. Let m be the mass of the rope and L be the length of the rope. A rope of mass m and length L is placed on smooth horizontal surface and pulled horizontally by constant force F. Find tension in the rope at a distance x from right hand. I'm defining x equals 0. This is x equal to L. Okay. Now it's asking to calculate the tension at a distance x here. Quite natural. Will there be tension? Yes, there will be tension. So what you do is like you just break up this. Can we break up things? This will be F. And this will be tension. So now, will all the parts of rope will accelerate, or only few parts will be at rest, or few will be in motion? All the parts of the rope will accelerate. No, what is the acceleration of this part? There will be the acceleration of this part also. Let the mass of this part be m1. Let the mass of this be m2. Similar to two blocks one. Then let's calculate F minus t equal to m1a, t equal to m2a. What is lambda will define? It is m by l, f minus t. What is m1? Lambda into x will be the mass of this part of the rope. What is m2? Lambda into l minus x. What is lambda into l minus x? Mass of this part of the rope. That is what m2. Then adding up this, f is equal to lambda l into a. What is lambda l? Is ma only. Okay, now I got expression for acceleration. What is that? F by m. Sir, we already know net force by mass. Okay, well and good. If you are able to make such a very clean observation, well and good. Start directly from there. Let me substitute this in the equation for tension. T equal to m2a, m2 f by m. What is m2? I'll bring once again. Lambda l minus x. What is m? Lambda l. No. Put x equal to 0. What is the tension? Will be F. What force you applied? I'm going to recollect back what I said. With what force you pull the rope, there will be the tension. Not if the rope is accelerating. If the rope is accelerating, then definitely the tension at this end will be F. What about, sir, tension here? Will be 0, no? Put x equal to L. If you put x equal to L, what is the tension? Tension at this point is 0. With what force you pull the rope, that will be the tension everywhere. No, at the end where you are pulling, that will be this one. Sir, like, I really want you to answer this question. Okay, you said, okay, what about this? Now I am pulling this end with a constant force F. Rope is moving or at rest?
Rest.
This is at rest. What about this rope? Moving. This is moving. And now what do you say about tension?
Will it be equal to force?
I want really students to answer this. As anybody is free to answer this one.
Sir, will it be equal to the force?
I don't know, pa. You should answer. You want to become engineer? You should answer. Definitely at rest, no, this rope or rope will move. Will be at rest only, no? I think all are sure, no problem. This is okay, fine. What about the tension?
Equal to the force, sir.
Equal to the external force.
Yes, sir, equal to the force.
Everywhere?
Yes, sir.
Everywhere?
Yes, sir.
Yes, sir. Ideal string means everywhere, sir.
It is kept on smooth surface, let it have a mass, no problem. Let it have a mass, no problem.
Sir, even also tension will be same everywhere.
Even also tension will be same everywhere. My question is tension, what happened to tension everywhere?
Sir, the other end is smooth.
What about?
The other end. Smooth. It is smooth.
Are you not seeing wall connected to wall? Please understand question. I took rope, I connected to one end of the rope to the wall. The other end I am pulling by a force F. Ground or horizontal surface, what will be that? Tension will be same at all points. Tension here. So if you choose A, B, C. So don't go for generalization. Sir, tell me one formula, I'll apply everywhere. Those days gone. You are in college, that you are in class 11, that you are taking for coaching for IIT, JEE, JEE Mains, Advanced, NEET, all the exams. So don't expect like one formula is there, sir, tell me one formula, I'll apply everywhere. First of all, come out of that approach. Come out of that approach. There is a very wrong way of analyzing things. Still somebody will, they'll message, sir, why don't you give us an idea so that we can solve all problem. How it's possible? I can just share some methods, like, okay, if you come like this, so tomorrow they may ask in exam some new thing. You should know all these basics and you should apply it. Tension will be same, equal to F. This little bit difficult. Okay, sir, like you said, okay, we'll accept, that's all. But sir, like, still, can you justify your answer? You are giving like an answer, that's all. But where is the justification? Yes, really some explanation is needed. Mere I'm just writing condition, that's all. Tension will be same at all points. Why? Then what you should say? Go home. Or sorry, you are already at home. No? At home, buy one rope, tie to the window, pull it. Then you see tension everywhere. This should be the one standard reply from teacher. In spite of this, as we can explain. Now the same problem, let me show it in other way so that we can analyze easily such conditions. I will come back to again this diagram. So instead of this, let's our approach be of this one. So let the force be F. Here there's a tension, there's the X, then this will be dx. The tension here will be T, will be T, because I gave this method, no? On any small part, the tension should always act away from the body. So what is this small? There is a small element. On the small element I have to show that. Then if I show T and T, okay, fine, then what is the net force on the element? 0. Then how come it will move? So definitely, what do we expect tension? Where it should be more, on the right hand side of the element, on the left hand side of the element? Yes, the tension should be T plus dt. Then only the net force non-zero, then only this element will accelerate. Otherwise, if you just write T and T, not justified. But okay, look at now. The very few best condition, or a very good condition is there. Altogether, as x increases, the tension is decreasing here, no? As x increases, the tension is decreasing. Because x you are going to measure towards left, and as you move from left to right, the tension decreases. So therefore, this will be dt is equal to dma. Or if you are getting confusion, its best way of writing this equation is t plus dt minus t equal to dma. T get cancelled, so dt dma lambda. This will be very troublesome, but your mathematics has to come into picture. So why negative sign? Because as x increases, tension decreases, or dt by dx will be negative. Therefore, I am bringing negative sign here. So further this dt equal to minus lambda. Let's go for limits. At t equal to 0, the tension, at x equal to 0, the tension must be equal to F. That's all. No, here what is the tension? Here it should be F.
Only, sir.
Then here it should be X. At X, let T be the tension.
Zeros.
So this will become T minus F equal to minus lambda A X minus 0. What is lambda? Lambda is m by L. What is x? X is f by m.
Sir, minus fx fx by n. Sir.
Here negative sign I forgot.
Minus.
1 minus it should be. No, I think still my answer is correct, no?
Yes,
L
sir.
minus x by FL. I'll write it in that form. I'm going to show the complete description. This will be the other approach. Mathematical approach will help you a lot. Okay, now I can justify. Now I can justify it.
Sir, here this object is placed on the smooth surface or on the walls?
On the smooth surface, the same
Okay.
thing. Okay, you want that. And now can we justify our answer? You take small element, then everywhere T and T, it will cancel out. T. So net tension should be 0. No, the tension you have to break up like this way. This is the best method. You break up here.
Sir, you have substituted the limits, no, sir? dt.
Okay.
Sir? You have substituted limits for dt, no, sir?
Tension here. At x equals 0, tension is F, and at a distance x, the tension is T.
Oh, okay, sir. Okay, sir.
Now I can justify clear. I'll take small element. What should be the tension? Because what was the purpose? We have to justify this one, no? I'll do justify it now with this mathematical thing. What we know it. This I think totally different one. I will. No, the same thing. I'm going to break it up. Tension at A is I need it. I'll break it up. Let's see. I'll pull this with a force F. Just only for our analysis purpose. So here what will happen? The tension will act here in this direction. Then what is the state of this element? Is at rest. This is at point A. Then here tension will act in this way. Then what is the state of this? At rest. At rest means then F minus T should be 0. So T equal to F. Sorry, you similarly break up here also. We'll see it. Oh, we can't do. Yeah, I'll bring another one. Let's break up at C also. Then we'll see the what is the net force on this? It is also at rest. Then air reaction also. Let's find out. Let's see what do we get. This is also at rest. Okay, are you getting now? We have to make observation. There's no other way. You have to make observations minutely.
Sir, reaction must be equal and opposite, no, sir?
Reaction, okay, R equal to T.
Sir, but they are opposite now, sir.
Let it be, no problem. That is what R is a reaction by the wall on the rope I am showing. If that is the case, if you are getting confusion, I have to remove this. Okay?
Yes, sir.
Sir, can you scroll a little bit up, sir? Yes, sir. 1 minute, sir.
So getting the idea?
Yes, sir.
See, kinematics was easier, some equations, some mathematics, but here we should be more near to the physical world. That's why from the beginning, very first class, I was insisting you. The more you are aware of the physical world, the better, little bit easier, things are easier for you. You can gradually improve the things. Time, what will happen? As you delay things, the more and more you delay things, the worse things you are going to face. Lambda is mass per unit length. Nothing is there. Lambda is ratio of m by L. So at least please do realize, nothing to do, one string, how much it will cost you. Some string will be there in your home. Make observation. Okay, fine. We'll end up the class.
Sir, lambda is linear density, no?
Linear mass density it is. Okay, kids, like we had the discussion about the some tension, monkey climbing up the rope. So these are the things and the spring balance also you have come across. So please do think, put effort, analyze, understand, and all these what all I discussed, nothing, you don't need any research lab. You just need some part of a rope, some different shaped blocks, then spring balance around some 60 or 80 rupees you are going to get spring balance. Take help of all that and try to analyze, think on that one. It's become very interesting. You feel that, oh, this is what I am learning. The interest will come for you. With interest, when you come to the class, you'll start making observation. Through observation, you'll start learning things. The knowledge acquiring skills will improve. Then you'll be in comfortable position. So we have an opportunity. It's not that like all these are high level, sir, we can't invest that much of money. Yes, we have an opportunity. Please put effort to learn things. Not like I'm not saying do hard work. I'm asking put effort to learn things here, not like just mere learning. Okay, we'll end up the class. Thank all of you.
Thank you.